In this video, we're going to continue solving for fundamental problems for statically determinate structures. Before we begin, our assumptions for all the problems in this video will be our moment will be assumed positive as counterclockwise, and we can have positive left to right in the x direction and positive going up in the y direction. Okay, so let's solve our first problem. So for this problem, we need to determine our direction components at all points, BC, AB, and this vector is at 60-degree angle. And for our uniform distributed load, let's convert it into point load. So it'll be 10 kilonewton per meter times the distance of the uniform load. That's 2 meters, comes 20 kilonewton. And this 20 kilonewton will be halfway point for our uniform distributed load. So in this case, it'll be 1 meter from point A. Okay. Now let's take the moment about the point A. And the first vector we encounter is point load, and it'll be negative because it's in counterclockwise direction and it's 1 meters away. And then for force BC, we only need to worry about our y direction vector because x direction vector is at the same level as the ax vector, and therefore they cancel each other out. So this will be positive FBC sine 60 degrees. Solving for this, you get force BC as 20 divided by sine 60. Oh, and another thing I just noticed while I was calculating, we missed the distance between the points, and that is 4 meters equals to 0. In solving this, we get 5 over sine 60. We'll solve for 60 later on, but we're going to leave it as expression for now. Okay, now that we have our force BC, we can also take a moment about the point C in order to find our value for point AY, or vector AY. So it'll be positive 20 times 3, and then negative AY times 4 meters equals to 0. Solving this, we get our AY as 60 divided by 4 is 15 kilonewton. Okay, now that we have these two, I'll just write it on our free body diagram so we know what we have solved so far. And our FBC is sine 60. Okay, all right, so we need now missing our reaction AX. Okay, so let's solve for reaction AX. So it'll be sum of forces in x direction. We know our AX is positive, and we're assuming reaction for force BC is also positive, so it's be sine 5 divided by sine 60 times cos 60 equals to 0. Solving this, we get AX as negative 5 divided by sine 60. We get 2.89 kilonewton, or we can say that we took the wrong assumption for our vector direction. If we have it in right to left direction, then it's 2.89 kilonewton. For point C, we know that whatever reaction, because there is no other reaction or force acting on the member BC, we know that whatever the reactions are for point B, it'll be same for point C. Therefore, we can write reaction BX is equal to CX, and our reaction BX is sine 60 times sine 60. These two cancel out, 5 kilonewton. And then our reaction BY is equal to reaction CY, which is 5 sine 60 degrees times cos 60 degrees equals to 2.89 kilonewton. For this problem, we have to determine horizontal and vertical components at the ruler's put at A and fixed support at B. Okay, so let's draw a free body diagram of the member AC. So for member AC, we have a point load, external point load, 10 kilonewton at 1 meters. And then because we know that it's a roller support at A, there's going to be only one vertical reaction. And at C, we can assume that there's only going to be a vertical reaction as well. Actually, we're going to do, because we also have other member, CB, so we also can assume that CX exists for now, or we'll see if there is a need for to calculate reaction in the X direction or not later on. Okay, all right, so let's take a moment about the point C. So first we have counterclockwise 10 kilonewtons times 3 meters, and then we have clockwise AY, and it's 4 meters away, equals to 0. Solving this, we get AY as positive 30 divided by 4, and this comes up to 7.5 kilonewton. Okay, now let's take a moment about the point A. So this time we have clockwise point load, and it's 1 meters away, and then we have counterclockwise CY, counterclockwise CY, and it's 4 meters away. Solving this, we get a reaction CY as 2.5 kilonewton. Okay, all right, so now that we have all the possible reaction forces that we could have gotten from member AB, let's focus on member CB. And let's draw the free body diagram for CB. So for CB, we have a distributed load. This would become 16 kilonewtons because our distributed load is 2 meters wide. So 8 times 2 is 16 kilonewtons, and it'll be halfway between these 2 points, C and B. So 1 meter on each side. And then we know that our reaction force C will be opposite of whatever we have in the AC free body diagram. So I'll draw those. And then for B, we know that because it's a fixed support reaction, we're going to have 3 reactions here. So you're going to have a vertical reaction, horizontal reaction, and a moment at B. All right. Okay, so that's all for this. So first of all, let's take our... Well, first of all, let's do the easy part. Let's sum the forces in X direction. Solving this, we know that we can assume our Cx as 0 because there wasn't any reaction acting on the point load A. So therefore, all the reactions are working in the vertical direction. Therefore, Cx is 0, and therefore, because there is no reaction that is acting in any other direction than vertical direction on member CB as well. So therefore, our Bx can be assumed as 0 as well. We have symmetrical loads here. We can sum the forces in y direction as well. And solving for that, we know that our point load will be negative, and our Cy is going to be negative 2.5. And then our By is going to be positive, equals to 0. Solving for these two, so 16 plus 2 is 18, so 18.5 kilonewton in the positive direction for By is our answer. Okay, so now that we have solved for that, now we need to solve for our moment. So for moment, we can take the moment about the point B. So first of all, we know that there's going to be moment B at point B, and then we have a point load 16 that's going counterclockwise, and it's 1 meters away, and then we have our point load or reaction force at Cy is going counterclockwise as well, and it's 2.5, and it's 2 meters away, equals to 0. Okay, and then our moment at B would be negative, so 5 plus 16, 21 kilonewton per meter. And now we know that our reaction here is negative, therefore we can say that we assumed our traction for moment to be wrong, and we can change it to clockwise direction, and this would become a positive. For this problem, let's draw our free body diagram. Let's do it for member AB. We have a point load halfway through, 300 pounds. And then we know, because the A is a pin connection, there's going to be both horizontal and vertical reactions. And for point B, we're going to have another force reaction, force BC, and we'll have horizontal vertical reactions as well, which we'll solve for later on. Okay, so let's take a moment about the point A. So our point load is counterclockwise, so it will be negative 300 pounds, 2 feet away. And then for our force BC, we need to find vertical and horizontal forces. For that, we'll need our distance between point A and B. Let's use Pythagoras theorem to find our hypotenuse. So it'll be 3 squared plus 4 squared, which is 25 square root. And square root of 25 is 5, so it'll be 5 feet. Okay, so, and we know that these reactions would be as follows. And for our x direction, we're going to have negative force BC and it'll be 4 divided by 5 times 3 feet. And then we can have negative force BC for our vertical component. It will be 3 over 5 times 4, all equals to 0. Okay. All right. Solving for BC, we get 600 divided by 24 times 5, and this comes up to 125 kilonewton. So that's our force BC, 125 kilonewton. Now we can find our force AX and AY, because these loads are symmetrical, we can simply take sum of the forces in x direction. So it will be AX, take away force BC times 4 over 5 equals to 0, and solving for this, we get 100 kilonewton. Similarly, taking the sum of forces in vertical direction, you're going to have AY as positive, point load as negative, and our force vertical component for force BC will be negative 125, 3 times 5 equals to 0. Solving for AY, we should get 225 pounds. Alright, now that we have those forces, we just need to find our forces for point pin spot C. And we know that whatever reaction forces are being exerted by the point B, that will be our forces for point C, because there aren't any other external forces acting along the member BC. So therefore, our BX is equal to CX, and our CY is equal to PY. For our next problem, we have member AB and BC, but our joint B is fixed connect. Therefore, we can treat this whole structure as one. So let's draw our free body diagram. we have a vertical point load of 6 kilonewton 2 meters away from point A, and then we have a horizontal point load 2 kilonewton 2 meters away from point C. We're going to have reaction forces. We are only going to have vertical reaction force for point A, and we're going to have both horizontal and vertical reaction forces for point C. Let us take the moment about the point C. Our first load we encounter is a point load 2 kilonewton, and it's going counterclockwise, so it's positive, and it's 2 meters away. Then we encounter vertical load doing counterclockwise, 6 kilonewtons, and it's 2 meters away as well. And then we have our vertical load at point A, which is doing clockwise, so negative, and it's 4 meters away, equals to 0. Solving for AY, we get 6 times 2, 12, 4, 12, 4, 16, divided by 4. So that's 4 here. So AY is 4 kilonewton. Now we can sum the forces in X direction to get the value for AX, or horizontal component at C. So we have positive Cx and negative 2 kilonewton. Solve for this, we get Cx is equal to positive 2 kilonewton. And we can use the similar method where we sum the forces in vertical component to get the value of Cy. So we have Ay, which is a positive 4 kilonewton, plus we have a negative 6 kilonewton, and we have negative Cy equals to 0. Solving for Cy, we get -2, -2, and it becomes -2 kilonewton.